Okay, self-starting. Okay, so there are two more slides that I didn't get to last lecture that I really want to, because there's a cute story for that as well. Plus, these details are necessary to go from a suffix array to a suffix tree, and to do other algorithms with suffix arrays instead of suffix trees. So this additional array, which I mentioned I named before, is called the LCP array, stands for longest common prefix. And in order to get to it, we'll define h of k. Visually, this will be a lot easier after anyway. H of k is the length of the longest common prefix of suffix k. So we know what a suffix k is inside the string. And some other suffix. Which other suffix? It's the suffix that is named just before k in the suffix array. Okay, so here's the suffix array. Okay, and if I want to know the height of, let's say, 8, okay, I want to know what is the length of the longest common prefix of suffix 8, that's my k, and the suffix that's located one position before k in the suffix array, which is 11. All right, so 8 and 11. Again, I mentioned that even though we would do work, the actual algorithm would be on a suffix array, it's really useful conceptually to look at the suffix tree. So 8 and 11. Here's 11. Where's 8? Take off my glasses. I can see it. Yeah, there. And the length of the longest common substring, the prefix of the suffix k, and the suffix located. So 8 and 11, that's length 1. And so 8, and you look down here, well, these are actually the h values. H of 8 is 1. Okay, have I confused everybody enough? So another way of thinking about this is, remember how I told you you can get the suffix array from a suffix tree. You just do a lexicographic depth-first traversal of the suffix tree, and you'll pick up the suffix array. So 2 consecutive entries in the suffix array are the 2 consecutive leaves that are visited in that depth-first traversal. So we have this depth-first traversal. Remember, it's lexicographic. So you visit 11, and then the next one you visit is 8. And that's why 11 and 8 are neighbors. Okay? And the longest substring that begins, common substring that begins at position 8 and also position 11 is the string that you read on the walk down to that node there, the lowest common ancestor in the suffix tree of those 2 leaves, the leaf 8 and the leaf 11. Okay? All right, so I'll say it another way. I'm going to say this 2 or 3 times because it's the key thing. If you have the suffix tree, we get a suffix array from it by doing a lexicographic depth-first traversal. And when you're doing that traversal, you come down to a leaf, 9, and you walk up to some point where you start going down again. At that point, that is the longest, that is the substring that begins at position 9 and also at the next position you're going to run into, which is 10. That's the longest substring that's common to both of those, and the depth down there is that length. Okay, everybody clear on that? So another way of saying this is, if for each consecutive entry in the suffix array, I also told you on the suffix tree what their least common ancestor was, what node is common to both of them and as low as possible, that's the information we want. Okay? And it's encoded in this h, and then if I organize the h's, the h values underneath the corresponding entry, that's called the LCP array. Okay, but I just think of it as the h value. Okay, so if I'm given k, like 4, I know I'm beating this to death, but k is equal to 4, its predecessor in the suffix array is 7. Why is it 7? Because in the lexicographic depth-first search, we went to 7, and the next thing we went to was 4. And here is where we move from going back up to where we start going down again. So this is the longest substring that's common to the substring starting at 7 and the substring starting at 4, and that depth is 2, and so 7, let's say 4, there's the 2 underneath it. Okay? All right. If you have the suffix array and you have the LCP array, or you have the H values, you can build the suffix tree. You just sort of think in reverse of what I was just telling you, okay? Because it's telling you for every successive, each neighboring pair of indices, how far up, where does their agreement stop? And anyway, as a homework exercise, you can devise a linear time algorithm to use this information and to reconstruct the suffix tree. And what I advertised earlier was that every fancy algorithm or cute linear time algorithm that's known for suffix trees has been implemented now in suffix arrays and LCP, if you have those two pieces. And what's the actually we call it constructive, what's the simplest proof of that is that, well, you could obviously take the suffix array and the LCP and build the suffix tree, which I just said you could do in linear time, and then from there run the algorithm on suffix trees. But consistent with the goal of building a suffix array without building a suffix tree, and therefore in smaller space, we want to only run those algorithms on these two. And we also want to build the LCP in linear time given the suffix array and given the string. So we don't want, even though I defined it in terms of the suffix tree, it's visually clearer, I want to be able to find this array, or another way of saying it, I want to find these H values without having the suffix tree. Okay. So this was an open goal for many years, and just as the question of finding a suffix array without building a suffix tree was open for many years. But it turns out that there is a linear time algorithm for this, which I'm going to show you, and it really is just a twiddle on the two-fingered approach. So if I I had 11 and 8 or something. Okay, so here's position 11, here's position 8, and I want to know what is the length of the longest substring that begins at 8 and begins at 11 that are identical. Well, the obvious way to do that is with two fingers. You compare the character at 8 and 11. If they're equal, you move over and compare 9 and 12. And if they're equal, you move over and you keep moving over until you find one that's not equal. And there you have H of 11. Okay? So just, if this was A, X, and this is A, B, then doing that, H of 11 would be equal to 2. Okay? So, but we have a linear number of, we have n pairs that we would do this for, and even though this is a small match in this little example, it could be something proportional to the length. And so that would be something that's all we can prove about it is n squared. In fact, we could make up examples where it's stated n squared in that example. But, so that's the obvious algorithm. It works. I mean, everybody recognizes that it works, but it doesn't run in linear time. Now I'm going to add in a little twiddle to that algorithm that's going to make it run in linear time. Okay, and it's this idea. Okay, so we're going to compute H1, H2. Actually, no, yeah, H3. So H1, I was about to say, no, we don't need 1, but 1 could be somewhere in the middle here of the suffix array. And then its neighbor could be like 26 or something. Okay, so we're going to compute these H values in where this index is increasing. Okay, so we're going to, in terms of the two-fingered approach, it's this one and then what is its predecessor, 26, and et cetera, and then for 2 and whatever its predecessor was, and so on. And so the left finger is moving over by 1 at each time, or it's moving left, that's moving right after each iteration. The right finger jumps all over the place because it depends on what the predecessor in the suffix array was. Okay, but here's the key idea. If, no, it's written here. Suppose we've computed HK. Now HK could either be 0, which means that there's no agreement between those two substrings that we're looking at, in which case the next thing we do is back to our 2 fingers at position k plus 1. But if it happens to be something bigger than 1, then when we want to compute the next one, hk plus 1, we can skip over h minus 1 characters before we start character comparisons again. Okay? And see the picture I'm going to write up here. I got a little bit rushed. So again, think of it in terms of suffix trees, even though we're not going to actually be on suffix trees. So here's k, and its predecessor in the suffix array, let's say, is j, because again, it's this lexicographic depth first traversal. You j, and then you come back and you get k. So in the suffix array, we have j and its predecessor. We have k, and its predecessor is j. And here's this is depth h. Okay? So that's the picture we're looking at. H of k is equal to little h, which is bigger than 1. And I claim that then when we look at k plus 1, didn't plan my space well. This is the suffix array. Here's k, and its predecessor is j. Now where's k plus 1? We don't know. I mean, it's in the array somewhere, but I'm not saying it's anywhere close to this. And what is its predecessor? We don't know that either. Okay, good answer. Everybody got that right. There's nobody, so I'll just call that j prime. Okay, and we don't know any relationship of j prime to j. Okay. Okay, so we have that. But one thing we do know is a relationship between k plus 1, and that's one of the things we want to understand, and j plus 1. Okay? Now this is not what we want. We want j prime. But here's j, and j plus 1 is here. Oh, sorry, that was in the suffix array. Now I want to show you the string. This is s. Here is k. And again, we don't know where j is. It was the predecessor in the suffix array, but in terms of s, it could be anywhere. Let's say it's just pictorially there. Okay? We know that the length of the longest common, the substring that starts at k and the substring that starts at j, that's h. That's length h. That's what we learned here. And h is bigger than 1. So what is the length of the longest substring that starts at j plus 1 and k plus 1? It's h minus 1. Okay, it's exactly h minus 1. So, and the key, so between k plus 1 and j plus 1, this is length h minus 1. Okay? Now, where in this picture, this is the punchline, where in this picture is j prime? Okay? J prime, remember, is the predecessor of k plus 1 in the suffix array. So j prime is the leaf that you visit before you visit k plus 1, leaf k plus 1. Okay? It is, remember, to get the suffix array, you're doing a lexicographic depth first traversal. So J prime is, and this, remember, is the least common ancestor of k plus 1 and J prime. But this is a common ancestor of, so J prime has got to be down here, okay? And this has got to be above this point because this is a common ancestor of both J prime and k plus 1. Picture tells everything. Is it? Everybody get it?
Why is J plus 1 a common ancestor? Why is J plus 1 an ancestor of J prime? I mean, you've drawn it that way.
What?
Why is J prime and then, I mean, why is J plus 1 an ancestor of J prime?
Okay, so yeah, so we really want this. This is what we want. And we already have J and K. And J and K, that goes down H, okay? And so I know that J plus 1 and K plus 1 is going to be H minus 1. All right. Now, so what? J prime is the leaf you visit in your lexicographic depth first traversal just before you visit k plus 1, okay? So where is J plus 1 in this picture? I claim it's above here, not down in here, okay? What would happen if J plus 1 was in here, okay? What would happen if J plus 1 was in there? Then, remember, our lexicographic depth first traversal goes this way to J prime, and then it comes up, and lexicographically comes down to k plus 1 is what we know. Oh yeah, but then the length, the common length between J plus 1 and k plus 1, that common length would be bigger than H minus 1. And we know that the common substrings from J and K were greater than 1, greater than 0, greater than or equal to 1, greater than 1. So this has to be equal, A here, A here. So if J plus 1 was down here, then the agreement between J plus 1 and K plus 1 is bigger than H minus 1. And then you add on the two characters at the left, the position J and the position K, which are equal. And therefore you get a substring starting at J and a substring starting at K, which is longer than H, which is a contradiction. So, did that make sense? Okay, one yes, one maybe. Okay, so yeah, that's a good point. I really have to say, and I did, rigorously, that J plus 1 is up here, is above the least common ancestor of J prime and K plus 1. And this is what we want. So the conclusion here is that H of K plus 1 can skip over H minus 1 characters before we start doing this naive comparison again. So I've just computed the length of the longest one from K and J, and that was H. And now I want K plus 1, and wherever J prime is, okay? But what I'm saying here is this can skip over. Instead of doing my two fingers from K and J prime, I can skip over H minus 1 places and start my comparisons from there, okay? So it sounds like a good heuristic, sounds like a good thing to do. Why does it give us linear time? Well, as I was saying in the naive approach here, the left finger always moves left to right. The right finger jumps all over the place. But every time we have one of these speed ups, both fingers, the left finger as well as the right finger, can move ahead well, the left finger in particular can move ahead h minus 1 spots before it starts doing comparisons again. So the progress that my left finger makes is proportional to the number of matches I had before, plus the number of iterations. Number of iterations is just the length of the string, and there we have linear time for building the h values, and therefore linear time for building LCP. Okay. I have a video of this, as I'm mentioning, where at the end of it I say, I've taught this about 4 times, and each time I think it's going to be a lot easier than it came out to be. And now actually, this is probably the 8th time I've taught this, and I'll say the same thing. This is supposed to be one of those, oh, that's one of those cute little ideas. You go from the obvious n squared time algorithm down to something that's linear time just by this little observation on this tree. Okay, everybody will get this in the privacy of their own mind, but now to move on to the next lecture. Okay, Burrows-Wheeler. Okay, how many people here came to see Burrows-Wheeler? Let's see, read mode, full screen mode. So Burrows-Wheeler, how many people have never heard of Burrows-Wheeler? Oh, good. Nobody, or, oh, okay, one person who claims to do this. You what?
I think you'll get a different answer if you ask how many heard it.
How many people have heard of it? Well, that's good. You add those two together, you more or less get everybody. Okay, so this is one of those things that is running around a lot, and people are using it, especially in computational biology, bioinformatics. I don't fully know why. I agreed to talk about this in order to learn all of those things. Okay, now Dick Karp, I was saying this earlier, Dick Karp in his 80th birthday celebration was talking about being asked to give a lecture on the PCP theorem, which was written up in the New York Times as the most profound theorem in all of computer science. And, but he actually didn't understand it. So he spent the night before cramming to try to understand enough to be able to give this lecture. So I figured, well, if Dick Karp can do that, then I can do that too. Anyway, the Burrows-Wheeler transform is something that's used in data in compression. Lumpel-Ziv we talked about earlier. This is something else that's used in compression. It's old. I don't know when it was first originated, but it was actually not well known until more recently, maybe 10 years ago or so. And we had a visitor from Poland in my department about, I don't know, 15 years ago or something. Anyway, while he was at Davis, he was writing a book on data compression. And it was all information theoretic and it's very, very deep and mathematical. And he presented it to me on his day he was leaving, and I said, oh, boy, and I can read this and I can finally understand Burrows-Wheeler because I know that's very important in data compression. He'd never heard of it. So I felt like, oh, my God. This is, the major thing. This is the CRISPR of data compression, and he hadn't heard of it, yet his book is just coming out, and what a shame. Okay, so I'm trying to stall here. All right, so let me try to tell you what I do understand about this, and then just inspired by what Pavel is going to be doing, we could have a flipped, where all of you are ready to talk about it and educate me. Okay, so given a string S of length n, the Burrows-Wheeler transform is a particular permutation of S plus one more symbol. Not very compressed if you have to have all the symbols in S plus something. Now, what is that actual permutation? You consider all the rotations of S. So you've got the string S, and you rotate it by one position, rotate it by two positions, and so on. So you have n rotations. And so imagine each of those, you've generated each of those, and now you sort them lexicographically into a matrix M. Okay? And then the Burrows-Wheeler transform of string S is the string consisting of the last character from each string in M going top to bottom. Okay, let me give you an actual picture for this. We'll come back to here. So if my string is Mississippi with a $sign at the end, then I'm going to consider all of the rotations of Mississippi with a $sign, and I'm going to sort those lexicographically. And remember, $sign is the lexicographic smallest character. So this is the lexicographically smallest, and then this is the next lexicographically smallest, and so on, all the way down here. I look at the last character on this listing. It's IPSS, and it didn't come out here, but that list, IPSSM, that string, which is formed from the last character of each one of those strings, each one of those rotations, is the Burrows-Wheeler transform of S. Okay, it's a permutation, obviously, of the characters in the initial string. Okay, so this has a very close relationship to suffix arrays. These are the rotations of the string sorted lexicographically. The suffix array shows you for each suffix of the string how they're ordered lexicographically. Okay? When I do a rotation of a string, the rotation starts with a suffix of the string and proceeds with the prefix of the string. That actually came up in one of the earlier lectures. Let me just put that out again. Now, there are a couple of pictures in dealing with this stuff that are critical, at least for me, to keeping my sanity in all of this. So here's S, and a rotation, one of the rotations would have Y and Z. It would have Y followed by Z. That's a rotation of S. Okay? So this is a suffix of S. Okay? So when I do the rotation, this suffix is now in the start, in the prefix. Okay? So if I'm looking at all the rotations and I'm listing them lexicographically, what wonderful coincidence occurs? Okay? Well, as I said, the rotation starts with a suffix of the original string. Okay? All the suffixes are of different lengths. You don't have ties between the lexicographic order of two different suffixes. They've got to be different because the lengths are different, if only because of that. So there's a strict ordering of the suffixes of the string. So there's a strict ordering of the rotations of the string. And what amazing coincidence happens between those two orderings? It's the same. Okay? It's absolutely the same. All right? So, and therefore, and then this is the shift. Okay, what is this? What is the last character in this rotation? So I'm going to call these things rotations. Okay, so we have S and we have rotations of S that are in capital M. Okay, what is the last character here? It is, this was a, this went this way and this way, so that's character over here, right? Okay, so the character, if this shift, if this rotation is actually equal to this suffix put in front, followed by that prefix, then the character here is the character here. Okay? And if the ordering of the strings in the suffix in the M, which we're using to define Burrows-Wheeler, is the same as the ordering of the suffixes in the suffix array, then what is this character? Okay? This is the character just before the suffix that starts here. So I can, this is at position 12. The first suffix is at position 12. So that starts at position 12. The character just before it is at position 11, and that's I. Well, there it is in the last position. Okay? Come down to here. This is, that's interesting. Let's say this one. This is, this is starts at position 9. This particular, this is a shift. This is a circular shift, which puts a suffix of s in first position. In terms of suffix arrays, it's there. And so this should be the 8th character in the actual string. So 1, 2, 3, 4, 5, 6, 7, 8. Proof by example. Okay, so I'm trying to motivate this notation up here, that I can find what character is in the kth position of the Burrows-Wheeler transform, and it's also sometimes called L of k, by looking at the kth entry of the suffix array. That's the kth entry of the suffix array is a position in the string s. Subtract 1, which means look one place to its left, and take whatever that character is in s. Okay, so all I'm trying to do is say you can build the Burrows-Wheeler transform, obviously in linear time, from a suffix array. You can actually go the other way as well. If you think about it, it's a little more difficult. It's a homework question. But so that they're equivalent. So this is my first meta question, which I always have come up with when there's this very large literature now built on Burrows-Wheeler transform. What advantage does it have over suffix arrays since the two are equivalent? Well, we'll get to that.
Space.
Well, not space, because actually the suffix array, I should have mentioned, here we put a dollar sign. In the suffix array, we wouldn't necessarily have that. I said a Burrows-Wheeler transform is a permutation of the original string plus one more symbol. Well, what the one more symbol is either a dollar sign at the end, or you can note which of these rotations is the null rotation, that is the original string.
But this is in alphabet of size sigma versus n. So you need log n for each.
We'll have to talk about that. It looks to me, at least at this level, at this moment, and without telling you anything more, a suffix array actually is one fewer character than a Burrows-Wheeler string, because the Burrows-Wheeler string will either have affixed an extra dollar sign or it has a pointer which tells you where the null rotation is. And why we have those I'll get to in a minute. Okay, so the key observation, this is seeing the relationship between suffix arrays and Burrows-Wheeler transform. This tells you how you can build the Burrows-Wheeler transform quickly. If a string s prime, oh, okay, sorry, I have to back up one thing. Now, since, these are ordered lexicographically, these are the rotations and they're ordered lexicographically. Obviously, all the rotations that begin with the lexicographically smallest character come together in one section. Well, there's only one of them since that's a dollar sign. But the next lexicographically smallest character is I, and all of those rotations come together, are in one section. So this is the I section, this is the dollar sign section, this is the M section, P section, and S section. And you can see they all start with S, these all start with P, and so on. So you can, the rotations divide into these sections. Everybody with me on that? That's key. All right. If a string S prime is the kth entry in the section for letter C, C is now a variable, not the actual letter C, then the left shift of S prime, moving it over by 1, rotating that way, will be the kth string ending with letter C in the entire list. Okay? So let's just look at this one. This is the second string. I'm really tempted to use this on here, but an amazing, after 2 years, nobody seems to have done that. This is the second string in the section for letter S. Okay? So I claim that the left rotation of this, which is the string ISSIPPI $MISS, should be the second string in M that ends with S. Okay? Well, where is this? Well, where is the second string that ends in? It's here. Okay? Which, as I said, was 1 over. Okay? Now, I'll give you a little argument for that. Oh, maybe I should give you that argument right now. This is, as I said, the first time I'm teaching this, so yeah, here's the key observation. This is just restating it. Okay, if rotation S prime is the kth entry in the section for letter C, then the left shift, call it S double prime, will be the kth string ending with letter C in M, in the entire thing. All right, so forget this pointer for a moment. Why? All right, so here we are in this is M, and here's C, okay? And you have a string here which is the kth entry in this section, okay? All of these strings in here begin with a C. So this is the C section. Okay? So they all begin with C, and when you do a left rotation, they all end with C. Okay? Now, ending with C, say that's where this guy went to. This one, when you do a left rotation, ends with C, and it's somewhere, that rotation is somewhere in the list. Okay? Now, who's above it here? These are strings that also begin with C, but they're lexicographically smaller than this one. Okay? So, since they agree on C, the part that makes them lexicographically smaller must be the remainder. So when you do the left shift, each one of these guys, this is going to be the start of some string, and it's going to be lexicographically smaller than the left. The left shift of this is going to be lexicographically smaller than the left shift of this. So this one is going to come somewhere above it. Now, the C section talks about what they begin with. So these shifts, they don't have to be in the same sections at all. But any string that was above the kth position in the C section will be above the left rotation, the left shift of this string. This left shift will be above this left shift. Okay? So all of those. And we're restricting attention to all of the strings that end with C. Well, a string whose left shift ends with C means it came from a string that began with C. So the only ones that are above the left shift that end with C are the ones that came from here. So if you're the kth entry in C section, you are the kth, your left rotation or left shift, you are the kth occurrence in M of a string that ends with C. Okay. Now, this is just saying the same thing. Okay. This is just writing up what I just said. And again, you can observe this. You can observe this in here. This is one of the keys for inverting the Burrows-Wheeler transform. Okay. So I said the Burrows-Wheeler transform is a permutation of the characters, permutation of the string, plus one more symbol, either a $sign that you put at the end, or a pointer which shows you where the where the null shift is. Probably other kinds of things would work as well. Because then the Burrows-Wheeler transform is invertible. You can go backwards from this string, which is I, P, S, etc. Remember, the Burrows-Wheeler transform string is just the last character here. This is all conceptual. This is so we can understand what's going on. And this tells you don't have to actually generate all these sequences and sort them, because you can get the last character here from the suffix array. Okay, but we want to go backwards. We have this Burrows-Wheeler transform string, and we want to go backwards. Okay, so there are various ways of doing this. The classical way that's described in the literature is not obvious that it can be done in linear time. So I don't like it. But it should be, let's try to use this to do the inversion. So let's say I have a pointer which is here, okay? So this is the pointer to the null rotation. And, oh, by the way, since every character shows up in the Burrows-Wheeler transform, why is that? We're rotating, we have all the different rotations. Rotation of 0, rotation of 1, rotation of 2, and so on. And then we're looking at the last character. So obviously, all of the characters of S, of the initial string, show up in the Burrows-Wheeler transform string. So we can go through there and we can count how many A's, let's say the string, the symbol is lexicographically smallest, and then how many B's lexicographically smallest, and so on. So we can generate these spaces. We know how big each one of these sections are and what section it is. It's the $sign section, the I section, the M section, even without having anything in here, well, except for we have that because that's the BWT string. Okay, everybody with me? Okay, so we point to where the null shift is, and we know what section we're in, and that tells us what the first letter of our original string is. Yeah?
So how do you know which section if you don't have the whole matrix? If you only have the last column?
Oh, that's what I was saying we do from counts. Okay, so the last column has every character in the original string. So we can go through that and count how many I's do we have, how many P's do we have, how many M's do we have.
And match them.
But
And match them with the last column.
No. Well, we're just going to, if we find out that we have, well, we only have $sign, so the first section is that big. Then we find out we have 4 I's, so that occupies the next 4 positions. And so we know that all the rotations that begin with I will be located here, even if we don't know what the original string is. Okay, so we know the sizes of all of these sections and what is the first character in that section. Yeah?
You can think of it as like a crossword puzzle, and you know, or something. You know that there's going to be 4 I's in that section. So you can just start filling in the stuff you know, basically.
Okay, if you want to think about the inversion as a kind of a puzzle, but yeah. All right, so we have a pointer to the start. So we know that our original string begins with this character, M. Okay? Now I want to get the second character. Okay? Where is the second character? The second character is the first character of the left shift of this. Okay? This is, well, it's $sign here. Yeah. This should tell you where the second character is. Okay? So if characters, so this is the first character in the section for M. Okay? So its right shift should be the first position of the section for $. That's what this says, right? Okay. If S prime, which is this thing now, is the kth entry, it's now the first entry, in the section for letter C, which is now M, sorry, then the left shift of S prime will be the kth, first, string ending with the letter C. Yeah. And letter C is M. Okay, so then we go to the. I can't do an example in real time at this point in my day.
Right above it. It ends with M. There is
Okay.
only one that ends with M. So that's the one above it.
Okay, so you're agreeing that this is right.
Yes.
Okay,
Shift, not question.
and that's the shift, and you just keep doing it, right? Because now you've shifted, and you know what section you're in, so you know what the beginning of that was. So after $, so, after M we have I.
I, and then there are 4 that end with I.
Yeah, as I said, after 3 hours of doing this, I can't do an example in real time. This is what keeps your sanity, okay? So, and this tells you how to get each successive character, all right? So let's say we've learned MISS, okay? So, MISS, so the rest is MISSIPPI, right? No, MISSISSIPPI, MISS, so we're here, okay? So this says if a string S prime, that's this one, is the kth, that's the third entry in the section for C, which is I, then the left shift of S prime will be the kth, third, ending with letter C, ending with letter I. Ending with letter I, so we have to find the third one that ends with letter I. 1, 2, 3. And yes, that is one shift over. Okay, so you just keep applying this observation, and you can read out what the original string is. This is I find this very confusing. You just have to, it's best if you do it when you're very rested, and there are other ways of doing this. This one you can implement in linear time, and we have pointers, which these are the strings, and this is the kth in section C. We said one shift. It should be the kth one that ends in C, wherever that happens to be. And we'll put a pointer from this string to this string. This is just one shift. Another way of thinking of this is a pointer from this string to one left shift over. Okay? But that's what we're chasing these pointers in doing this. So when you, if you built these pointers, then you can just run along them and you do the inversion that way. As I said, the classic way of doing this has to do with radix sort, but this is easy to implement in linear time. Here's an even easier way of doing this. But I was too jet lagged coming all the way from Davis to confirm this just before the talk when I was trying to think it through. But I think this is right. This is contributed by a graduate student. So last time I taught this, or the only previous time that I taught Burrows-Wheeler, I gave as a homework exercise how to do the inversions. And some students came up with this algorithm, some students came up with the radix sorting algorithm. Julia Matsieva came up with a clever, I think, algorithm, and you have to tell me whether it works. So she said, you go down the Burrows-Wheeler string, and you form a 2-character string, which is going to be the character in the Burrows-Wheeler plus its position in the string. So we have I1, and then we have P2, and S3, S4, whatever that happens to be, M5, and so on. So you have these two character strings. Then radix sort. Okay? Radix sort those and pay attention to where everybody went. Okay, so you'll have some new ordering of these, and then put a pointer from where it went from in this list to where it went into the radix sorted list. And I know that when she handed that in, it was a couple years ago, I looked at it and said, oh, that's great. Because then it makes it trivial that this can be done in linear time, and at that point, I was younger, I had a brain, and it wasn't after 3 hours of lecturing, and I could see that it was right, and Pavel just nodded that it was right, so it must be. Okay.
Well, I'm not clear why typical way to present it doesn't appear to be linear. I thought that's the usual way to describe it.
Well, I don't know. When I looked at the classic way that's in a lot of the books, it didn't look on the face of it linear time without additional data structures. It was just harder to argue that you could actually do it in linear time this way. But this one is clear because these guys are just constant space. Okay, so that's the inversion. Now, I've got 2 minutes to tell you why we care. Why do we care about Burrows-Wheeler? I mean, I have to tell you that I first learned about Burrows-Wheeler from Steve Skena. We were in a train going from Lyon to Paris, and he posed it as a puzzle. At that point, it was just a puzzle. How do you do this? And it was invented years ago, and it was just sort of a puzzle. What it tends to do, this is the claim, what it tends to do is group together common characters, equal characters. Okay, so if you have, as you do in DNA or in genomic sequences, a lot of repeated substrings, okay, well, the suffix array actually groups the first character of those near each other because those repeated substrings are equal for a while. The Burrows-Wheeler tends to group together the characters that are not necessarily at the beginning of those repeated substrings, the ones that are identical at position 2 and at position 3 and so on. That's another one of those things that I was going to really be clear on before this lecture, but again, after 3 hours of lecturing, it's just not clear to me anymore. It was, last night it was absolutely clear, so clear I didn't have to write it down. So you want to think about that. But the claim is that the Burrows-Wheeler transform, which is invertible, puts more identical characters together than in the original string, if there's highly repetitive substrings, as there are in DNA, as there is in DNA. And therefore, you can do a number of different compression techniques. The most obvious one is run length encoding. So you have a string, and it has 26 ends in a row. You can replace that by the number 26 and n. And the original paper, by the way, this pointer here I would call an FL pointer. In the original paper they call it an LF pointer. It's just they do the reverse, but it's, you know, we're pairing up entries here, and whichever way you want to direct that. And then this became an FM. So if you've seen papers that talk about using the FM indexes, that's all this is. They're using these pointers, or directed the other way. Why FM? This is the name of the authors, and I've forgotten what they are. 2 Italians. Yeah, what Ron said. And so that became in honor of their, and in their original paper, they have a lot of different ideas for how you compress the Burrows-Wheeler string. So the most obvious one is run length encoding, because you're going to have a lot of characters that are identical together. And another one is move to front. which also seemed, when I understood it, seemed to have some effect. But it seems to have dropped out of the literature, so I guess people have found that that wasn't so successful. And so the point is that you can compress Burrows-Wheeler string much better than you can compress the original string. And it's invertible, okay? And so what I was going to do next, when I've run out of time, is show you how you search in a Burrows-Wheeler string. So you have the Burrows-Wheeler string, which is a representation of the original Mississippi, and I want to find all the occurrences of ISSI, okay? But I no longer have the original here. Of course, I could just invert and then search on there, but the whole key is how do I search in the Burrows-Wheeler string? Which really means, how do I search in the compressed version of Burrows-Wheeler? Well, I've got to uncompress little bits at a time as I'm going. But if I told you the logic of how you search for a substring, it's a substring of the original S, but we're going to search for it in the Burrows-Wheeler string, then you can figure out yourself how you're going to open the compression as you need to. So what's the whole point of this is you get good compression of the DNA, which is in our community why we've done this, and you can search inside that compressed string for substrings just as fast, at least in worst case time, as if you had the original string itself. And you don't have to uncompress the whole thing. Now, the key to searching, I've really run out of time, and this works out really well, because I ran out of time in my preparation too. So the key to actually how you search for a pattern in Burrows-Wheeler is just these pointers again. These pointers tell you everything. So the high-level idea is that you have a pattern P, which is A, B, X, Y, Z or something. You have a last character. Here's again, the partition. I want to find the start position and the end position, a start and an end position that contains all of the substrings that begin with Z. This is a little confusing because we're going last to first, but now I'm talking about beginning, okay? So they begin with Z. Well, that's just the Z section. These are all the strings that begin with Z, okay? And then from that, I want to find all the start and end positions of all the strings that begin with YZ, okay? So what does that mean? That here are all the strings that begin with Z. Where are all the strings that begin with YZ? They're in the Y section. Okay? So these are strings that begin with Y. Some of those continue with Z, and some of them don't. Okay? Where's the first one that continues with the Z? It's wherever this guy pointed to. So this is the first string among the rotations that begins with a Z. So it is the first, whatever that mantra was. You just apply that. You know that you're going to be in the Y section, but you have to figure out where in the Y section you are. And that mantra tells you exactly where that should be. And you already have pointers that did that for you. So you follow that pointer, you get to there, you follow the next pointer, and that tells you the first position. The last position is symmetric, and you end up with the first and last positions in M, which means in the Burrows-Wheeler, which means in the suffix array of, once you've done all of those, of this string. This is we find the first and last positions of the strings in M that begin with A, B, X, Y, Z, which means we found prefix of suffixes that have that, which means we found occurrences. This is very, very rough. But again, these pointers, if you understand the mantra, then you understand the pointers. If you understand the pointers, then you'll figure out the algorithm. And that's about all I know. There is a book. It's very not well known, I think. There's actually a whole book on Burrows-Wheeler that was written a long time ago. And I don't know why it's not better cited in this whole literature. It's by, well, the only person I know in this is in 2008, Mukherjee in Florida. But they have here the Burrows-Wheeler transform of all of Shakespeare's Hamlet. Okay, and a little section, just a little section of it, and it's got 1, 2, 3, 4, 5, 6 lines long in here, about 80 characters across, and they're almost all ends. So it's just an illustration here that even in English, when you do the Burrows-Wheeler transform of a long enough string, you get a lot of grouping of identical characters, and then you do the run length encoding and you get a compression. I think I'm out of time, right?
Just about.
Yeah, I've lost track. I've hyperventilated and don't have anybody ask me anything. Okay, questions? Yeah.
So the original motivation for Burrows-Wheeler transform was to compress the string and
Yeah.
make it invertible. But it's not clear to me where explicitly in application, let's say to matching, this compression is used. When you look at bow tie,
Yeah.
pencil bow tie, it's not immediately clear to me why it is even important there.
Yeah.
So is it really used in DNA application framework? So it just kind of...
This is a multiple question. I know they don't have, the microphones here don't pick up the questions. One question, is it really used? Seems to be. There's huge literature on everything is done on the Burrows-Wheeler transform string. And Bowtie is a program that is heavily used and does that. And there are about 5 or 6 papers that I collected and I intended to read and understand before this lecture on using the Burrows-Wheeler compressed strings in sequence assembly, in read alignment, all the classical things that we do in computational biology on sequences. There are papers that show you how to do that using Burrows-Wheeler and claiming that that speeds things up by 100 times, reduces space by 100 times or whatever. And so that is the reason, if it's true, if they're right, and I don't have any opinion about that. Yeah.
So I want to go back to this point of space.
Of what?
Of the space.
Oh, yeah.
So if you're using the suffix array, you need log n bits for every entry of your permutation.
Okay.
If you're using Burrows-Wheeler, you need 2 bits for DNA. It's just a permutation of the text. So if the alphabet is small, it's a big say.
Okay, that's an interesting point. Yeah, I hadn't.
But this is a bit cheating because the part that you didn't show about looking for a match, you need to keep some of these pointers if you want to do this efficiently. So,
Yeah.
Because otherwise you find this segment, but you don't know the location of these ABXX XYZ in your text.
Right.
So you need to keep a fraction of the starting point. Just
Yeah. So there's a lot of engineering. So Ron's major point here, which I had not thought of, but is sounds like a good advertisement for Burrows-Wheeler, is that in the suffix array we're keeping numbers, okay? And what are those numbers? Those are indices from position 1 through n. So you need about log n bits to represent them. In the Burrows-Wheeler transform, we're just keeping characters that come from DNA in our application. So we need 2 bits for alphabet of size 4. And so that's already a big savings there. And then the additional compressibility is the next advertisement for dealing with the Burrows-Wheeler transform strings.
So the last column of the matrix is invertible.
Yeah.
Are there any other columns that are invertible?
Oh, okay. Are there any other columns that are invertible? I'm not sure. So in order to fully invert, you need either the $sign. That helps because that's always at the top, since the $sign is the smallest, or you need a pointer which tells you where you begin. So I did think about what if you don't have either. You actually can learn the string in circular order. You just don't happen to know where it begins. So that sort of is a hint that maybe you can get a lot of other information as well. But anyway, I have not thought that through.
Well, there's at least one more column that is in
The first one. Yes, you can get the first one.
The first one is not invertible.
It's the text, you mean?
No, the first column is ordering of
Oh, you're right.
nucleotides. So the first column is...
Oh, you asked which one's invertible. Yeah, okay, yeah, sorry. But the first one tells you, oh no, yeah, if you had the actual suffix array, then it's invertible. Well, that's all I know about Burrows-Wheeler. I was hoping that there would be a true expert here on Burrows-Wheeler who could truly answer the question of why is everybody talking about it. And, it's like, I don't know, pet rocks or hula hoops. I never really got into that. But, but I did like those hoverboards. I was thinking of getting one of them. But apparently they blow up, so anyway, thank you.